So hi everyone, welcome to the second video in our series. Today we're going to dive into a really useful skill, drawing graphs of functions. Now that might sound a bit scary, but don't worry, I'll explain everything step by step, including what linear functions are and the different types you need to know. So all you need is a notebook, a pen or a pencil, a ruler to draw your own graphs, or those worksheets or those copies that I distributed in class where you can draw your graphs of functions on. You can always pause the video, look at the question, see if you can solve it yourself, and then I will do it in this video. So without further ado, let's start. So before you start, if you don't know what this picture is for, I urge you to watch 11.1 functions. I explain what functions are, and you probably need to know about functions before you watch the second video. So please do not be lazy. Watch the first video, then move on to this one. All right? So for those who have already watched the first video, this is what we have. So this is a function, right? Y equals x plus 2. Now, we've already agreed that x usually goes here and y goes here. So x goes into the conveyor belt, comes out as y, and then a process happens right here in this box. And for this particular function, for us to get a y, we need to add 2 to x. So the function of this machine is plus 2. So let's try some values and see what we get. So let's start with the first value, which is, I'm going to pick -3, and you will see that -3 plus 2 is -1. I hope you all got this right. And then -2 plus 2 would give us 0. -1 plus 2 gives us 1. 0 plus 2, 2. So you might notice then that whenever we input a value, we always add plus 2 to it, and then it'll give us a value at the end. Now, would we be able to draw a conveyor belt in our quiz or on any exam for that matter? Well, of course not. So what is the mathematical way of doing things, or what is the best way to represent all of these possible numbers? Well, if you look here, it would be the table of values. And the table of values allows us to choose certain values for x and see what y becomes. So if x is -3, then y is -1. If x is -2, y is 0. For those unaware of how we got there, all we did was grab this x, we replaced it by something else, usually the number we're using. So instead of writing x, we wrote -2 plus 2 gives us 0. All right. So let's keep going then. When x is -1 plus 2, that's 1. When x is 0, it is 2. When x is 1, that's 1 plus 2, which gives us 3. And when x is 2, that's 2 plus 2, which is 4. And then when x is 3, 3 plus 2 is 5. Now, before we move to anything else, you need to be familiar with two things. These are coordinates, and these are points on a graph. And they're actually related to each other. Now, they might sound like difficult names, like difficult concepts, but really, trust me, they are not, and you will come to know why. So in here, I have these points. These are points A, B, C, D, E, F, and each of these points have coordinates. All right? These are called what? Coordinates, and we usually place them in between parentheses. So the first number represents x, and the second number represents y. So whatever number you see at the start, that's probably for x. Whatever number you see second, that's probably for y. Now, how can we place these points on our graph right here? And it's actually quite simple. You first start with the x-axis. If you're unaware, again, this is a graph. It has two axes. One is called x, the other is called y. If you know this already, then you have probably skipped me. But if you have not, thank you for not skipping me. Now, let's first look at the x-axis and let's see what number matches x for each point. So let's start with a. So x here is 1, and this is 1 on x. But then let's look at y. Y here is 2. So for us to plot the point A, we would first look at x. X is 1, right? X is 1, and y is 2. So we move up. So this is point A. Same here. B, x is 2, y is 3. So it's right here. So this is point B. Now, what about C? C is negative. When x is negative 1, y is 3. Negative 1 is right here, and 3 is up here. So this is C. For D, it's the opposite. X is 1, y is negative 3. So instead of going up this time, we would go down 3 squares. So D is right over here. Now x here is 0. So we're going to start from here. We're not moving either right or left. And then y is 2. So we're moving 2 squares up. So E is right on here. What about F? X is 2, but y this time is 0. So that means this time we will be moving twice to the right for x, but we will not be moving either up or down. So F will be right over here. As something extra, just to double check that you know everything, what do you think the point with the coordinates 0, 0 is called? Now, if you know, then congrats. If you don't, this point is called the origin. And this is very important for later explanations. So let's go back here now. So we know our function is y equals x plus 2. We've already seen the analogy, the example of the conveyor belt. We input a value of x. We can pick whatever we want. Negative 3 plus 2 gives us negative 1. Negative 2 plus 2 gives us 0, etc. We then placed it in what we called a table of values. And we learned that these points, the coordinates of these points, stand for x as the first number and y as the second number. Can you see the relationship between what I was talking about and what I'm talking about right now? If you have, good. If you have not, well, let's look at our table of values. That means that this is a point, this is a point, this is a point, this is a point, this is a, guess what? Another point. This is also a point, and this is a point. Good. The first point has the coordinates negative 3, negative 1. The second point has the coordinates negative 2, 0, etc. So let's draw each individual point and let's see what we get. So let me grab my pencil. So when x is negative 3, that means I'm moving 3 squares to the left. Y is negative 1, means I'm moving down 1 square. So this is my first point, right? Now, this is my first point. My second point is when x is negative 2, y is 0. I move 2 squares to the left. I don't move up or down, so I will stay right over here. When x is negative 1, right here, y is 1. I hope you understand this by now. When x is 0, y is 2. When x is 1, y is 3. When x is 2, y is 4. And when x is 3, y is 5. Aha! Our conveyor belt behaves in a way that we can say a lot about. The first thing is, when I put the x values and the y values into my table of values, and then I plotted the points based on this table of values, I can see that these points are aligned, huh? So what can I do now? Well, you connect the dots. So you grab your ruler, this is my ruler on my computer, and you try to align all the dots together, and if you've done everything right, they should be aligned. Now this, boys and girls, is a graph of my function. This is for y equals x plus 2. So what does that mean? That means we can either write the function as this, y equals 2, or we can represent it geometrically by drawing it as a line on a graph. So this is the fourth time I'm recording this video. I'm having a very fun Saturday night, so I would appreciate if everyone watches this, hopefully. But let me stop complaining for a bit. Let me talk about linear functions can have forms, huh? Well, you might wonder what linear functions are, right? Well, let's talk about that for a while. So we will keep with the same example of the conveyor belt, and we are going to dig deeper now because we are not only following steps to draw a graph, but we are trying to understand what we're drawing exactly. And what we're drawing is called a linear function. And the reason I know that this is a linear function, at least according to my conveyor belt for now, is that when I write the x's, and they are in order, I'm not skipping numbers, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, etc., I am getting negative 1, 0, 1, 2. And if you look at the difference between each two numbers, you would find that the difference is always plus 1. Plus 1 here, that does not look like a plus. Plus 1 here, plus 1 here, and plus 1 here. Now, so the output, the number we get at the end, there's the same difference between all the numbers, right? This is why we call it a linear function. But then you would ask, so what makes you know that what you're seeing in front of you is what we call a non-linear function? Well, for the sake of explaining things, I'll tell you. If I want to know that a function is nonlinear, I will simply do this. I will input the number 1, for example, and on this particular day, I'm going to work, I put number 1 as expected, and I'm probably expecting either something less or something more, but I got 1 here all of a sudden. I say, I don't usually get paid to do this. What if my boss finds out that I put the number 1, I got 1 in the end? So I say, you know what? Let me try with a different number, 2. And I'm expecting 2 things here. Either I see a different number, or I will say, hey, maybe the machine today is actually not doing anything. We're only adding 0 to 1. That means we're going to get 1 at the end. But this time, I got the number 4. Interesting. So I put the number 3, the input, and my output this time is 9. Wow, okay. But 4. 16. Huh? What's going on? So let me see what the difference is here. So to go from 1 to 4, that's plus 3. But to go from 4 to 9, that's plus 5. And to go from 9 to 16, that's a massive difference. I'm adding an entire 7. Now you might see a pattern that every time I'm adding 2 to the number I'm adding, but that's not what a linear function is. I'm supposed to be adding the same number every single time. And that's basically what a nonlinear function is. And you will see this more extensively in Unit 10. If you are curious what the function of this machine is, simply put, we are just squaring the numbers that we input, and we're getting the numbers we squared at the output. So 1 squared is 1, 2 squared is 4, 3 squared is 9. Now, what if I tell you that I can know that a function is linear without even having to look at my conveyor belt? All I have to look at is the graph of that function. So let's assume you've gone through all the necessary steps. You've seen what the function is. It's y equals x plus 2. You drawn your table of values when x is negative 3, y is negative 1, etc. You plotted all the points, you connected the dots, and you ended up with this, a straight line. This is a straight line. And a straight line is an indication that our function is linear. So we could say this. The line of the graph, or the line of the function, is a straight one. We can then automatically assume that this indeed is a linear function. Now, you don't have to write the word indeed, but this is a linear function. All right, so yeah, it took me 4 times to record this, but we finally made it. So in the previous part of this lesson, we've seen that if the line of our function is a straight one, that means our function is a linear one. But then we did not really cover the entirety of the title, did we? Linear functions can have different what? Different forms. How complicated can this get? Well, very complicated. But I'll walk you through it step by step. You don't have to worry about it. This is very good for you. Just follow the lesson, okay? So, let's start with functions in the form of y equals x plus c. Now, I hope I have explained this enough in class, but in case you forgot, no worries. You have a whole weekend to revise plus Monday. Now, what does c even mean? C stands for the word constant, all right? So, let's look at these functions, for example. Y equals x plus 2. Y equals x plus 4. Y equals x minus 2. And y equals x minus 4. Now, we've already drawn the first one. Y equals x plus 2 is represented on this graph right here. And as you can see, it is a straight line, therefore it is a linear function. But what if I tell you I can actually predict whether a function is linear or not without even having to draw it? And the way we are going to do this is by recognizing its form. What I mean by this is, c here can change depending on what your function is. For this case, for example 1, c is 2. For example 2, c is 4. Example 3, c is negative 2. And for example 4, c is negative 4. But what do they all have in common? Or how can we describe what they all have in common? Well, we can say that all of these functions come in the form of y equals x plus c, where c is a constant. Okay? So c could take on different things. Plus 2, plus 4, minus 2, minus 4, plus a billion, minus a billion. It does not really matter as long as it's in this form. But then, let's learn something extra together. How about this? Y equals x, and that's it. What do we do then? Y equals x. Is this really in the form y equals x plus c? Is y equals x a linear function? Well, what if I just do this quick magic trick? I will highlight my function. Y equals x plus 0. So c here is 0. So yes, y equals x is in the form y equals x plus c, but y equals x is a very special one, and you'll come to find out in the next part. Now, the last thing I'm going to talk about in terms of y equals plus c is another pattern that we see for all of these functions. And for this, I will use the help of my graphing calculator. This is desmos.com/calculator. And I will input all of my functions, okay? So y equals x plus 2, y equals x plus 4, y equals x minus 2, and y equals x minus 4. Now, remember this. C here is 2. C in the second example is 4. C in the third example is negative 2. And C in the fourth example is negative 4. Now let's look at each line. When C is 2, the line crosses the y-axis exactly at 2. Interesting. When C is 4, the line crosses the y-axis exactly at 4. When C is negative 2, the line crosses exactly at negative 2. And when C is negative 4, the line crosses exactly as negative 4. Now, then can you maybe predict what x plus 5 would look like? Where would it cross on the y-axis? If your answer was 5, then you're right. It does cross through 5. If it's x plus 6, same thing. If it's x minus 11, well, if I zoom out, you will see that it does actually cross minus 11. So this is the final thing that you need to know about functions in the form of yx plus c, or y equals x plus c. So to summarize, these are the things you need to know. Number 1, if the function is in the form of y equals x plus c, then our function is linear. Number 2 is y equals x is in the form y equals x plus c because y equals x is the same as saying y equals x plus 0. Third, when y equals x plus c, C is an indication of where the line of the function will cross the y-axis. So that means if c equals 4, then we are sure that the line of the function will cross 4. On the y-axis, of course. Now, if I was too fast on these things, this is why technology is a good thing. You can always roll back the video, you can slow it down, you can speed it up. It's up to you, but this is basically for functions in the form of y equals x plus c. We don't have much left now. Let's have a quick look at functions in the form of y equals mx this time. So, as you may have seen, this is for functions in the form of y equals mx. And let's first start with a question that says, draw a graph of the function y equals 2x. Now you should become familiar of the steps we take to draw this graph. And the first step would be to input different x values and to find what y is. So if I replace x with -3, y would be -6. And then if x is -2, y is -4, because -2 times 2 is -4. -1 times 2 is -2. 2 times 0 is 0. 2 times 1, 2. 2 times 2, 4. And 2 times 3 is 6. Then all we have to do is grab our pencil and plot our points. Isn't that right? So let's do exactly that. So when x is -3, that means I'm going to the left 3 times. Y is -6, it's right over here. All right. When x is -2, y is -4, right here. When x is -1, y is -2, right here. When x is -1, y is 0. Or sorry about that. When x is 0, y is 0. And where x is 1, y is 2. And when x is 2, y is 4. And when x is 3, y is 6. As you can see, again, our dots align. That means it is a linear function. I do not recommend get them line this thick, so let's unthicken it and let's connect the dots together. So we can already tell that the function y equals 2x is a linear one, remember? But then what if I tell you that it also follows the form y equals mx, where m stands for multiplier. M stands for what? Multiplier. Okay, that's the way to remember it. Multiplier. So there are functions that take the form of multiplying something by x. And examples of these functions are y equals 2x. We have drawn this already. Y equals 3x. Y equals -4x, for example. In here, m is -4. Y is -6x. Y is, let's say 5x, right? So let's highlight m for each one. So 2, 3, -4 here, not 4, it's -4, -6, and 5, right? But then I will add another one. Again, y equals x. Y equals x. Why is it not working? Y equals x. There we go. So does this follow the form of y equals mx as well? Actually, it does. Because if I do the magic trick again, we'll see that it's y equals 1x, right? And this is the special thing I told you about y equals x, because at the same time, it can take the form of y equals x plus c and y equals mx. And now let's try to input all of these functions into our graphing calculators, okay? So let's try to get them into our graphing calculators. So 2x, 3x, y equals 2x, y equals 3x, y equals -4x, y equals 5x, y equals 13x. I'll just input new ones, 20x. All right. What do you notice? They all go through the origin. This is the special thing about y equals mx. It goes through the origin. So if there are certain things we know about y equals mx, it's these things. Let's start. Number one, when the function is in the form y equals mx, then it is linear. All functions or all graphs of the functions that have a form of y equals mx cross the point 0, 0. Remember, we called it the origin. Number 3, y equals x is in the form of y equals mx and y equals x plus c at the same time, because y equals x can be written as y equals x plus c and y equals mx. Got it? I hope you have. So in order to answer this question, we will cover the first exercise of your learner book. And it says, for the function y equals x plus 1, we need to first copy and complete this table of values. All right? So let's do that. So every time we are replacing x with the value that I have given us, and we are trying to find what y is. So if x is -3, -3 plus 1 is -2. If x is -1, -1 plus 1 is 0. If x is 0, that's 0 plus 1 gives me 1. 1 plus 1 is 2. And 2 plus 1 is 3. And then I will have to plot all of my points. Isn't that right? So let me try to do that right now. So I'm plotting all of my points. Okay? -3, -2. So right over here. It's not working, huh? Now, one moment. Give me a second. How about this? So, -3, -2, right over here. -2, -1, right over here. -1, 0, it's right over here. 0, 1, this is here. 1, 2, this is right here. 2, 3 is right here. And 3, 4 is right over here. So let's connect the dots together. And this is the line of our function. Isn't that right? Now, as you may have noticed, I have taken a very long time to draw my graph. But what if I tell you that as soon as we know that this is a linear function, for example, y equals x plus 1. What form is this? Well, this is in the form of y equals x plus c. Isn't that right? Y equals x plus c, where c this time is 1. Right? Now, as soon as I know that this is a linear function, I can only draw 2 points and I will still get the same line. So let's say when x is 0, okay, y is 1. And when x is 1, y is 2. I've already drawn the 2 points here. I could just connect these 2 dots together and I would still get the same line. So this is why it is important to know whether a function is linear or not. So this is also something that you probably need to know. These are mainly questions C and D, and they read as, show that the point with the coordinates -20, -19 is on the line y equals x plus 1. This is the line that we just drew. And the second question says, is 2019 on the line y equals x plus 1, and give a reason for your answer. Now, a lot of you might have jumped to saying, okay, what if I just draw or plot the point -20, -19 on my graph and see if it's part of the line when I extend it with a ruler? But the problem here is you would have to go all the way over here maybe to see -20 and all the way down to see -19. And you would probably not have enough space on your notebook, right? So there is a way actually. So y equals x plus 1, right? And for c, the point is -19, -20. Or -20, -19, sorry. If you remember what we've done, we said that the first number stands for x, that means x is -20, and the second number stands for y, so y here is -19. For us to check if the point is on the line, all I have to do is replace the x with negative 20, so negative 20 plus 1. And if my answer is negative 19, then yes, the point is on the line. If the answer is not negative 19, then the point is not on the line. Now, lucky for us, negative 20 plus 1 is indeed negative 19, so the point is on the line. It's on the line. Now, let's look at D now. So they are telling us to check with the point 20, 19. So let's do the same thing. We replace x with 20, that's 20 plus 1, and the answer for this is 21. But look here, the point shows y as 19. So does it belong to our line? Simply enough, you will say that this is different from 19, and you will say, no, 2019 does not belong on the line.